All right, I've hit the start recording button.
Awesome.
Okay, so this is a follow-up to the last video where I hacked together a bunch of code in order to test out this Honeycomb code. And this time I've kind of polished up the code, fixed up some of the issues from last time, and also I have Michael Newman with me to comment on it. Like we're going to do a code review basically. Newman?
Hello.
Yeah.
It is.
All right. I guess for context, for people who have no idea who Mike Newman is, he's a coworker on the Google Quantum team, and I don't know. Did you want to give any amount of history?
I mean, I work mostly on quantum error correction. That's all you really need to know.
Yeah.
And this is really not a follow up to the last video, but it's a follow up to a follow up of a 4 hour video, which we have completely thrown out.
Yeah. It turns out that as things get bigger, they get harder to just hack on while you're recording, and it helps to go away and think on your own a little bit.
Yeah.
Anyways, uh, the first thing that we have to go over are the changes that we made to the code, which are really like superficial changes ultimately. So here I have the diagram that I made last time of the layout of things, where there's this hex grid, and they have the parity measurements being performed on edges of the hexes, categorized by their direction, so that like all the horizontal edges are ZZ measurements. Instead of making directions a consistent color, we decided to make the zeros, ones, and twos a consistent color, so that the zero hex, for example, would be the XXXXXX stabilizer hex. Also, we squared off the coordinates. So this is oops, that's the wrong one. That's also the wrong one.
You're giving away a ton of information early.
Yeah. Um, so this is sort of the squared off coordinate system that we're going to be using with these consistent hex faces. So for reference, red, green, blue is X, Y, Z. So red is X, green is Y, blue is Z. Where X, Y, Z, I mean the Pauli operators. And sorry that I have like little scribbles all over these diagrams. I was using them for thinking, and I didn't erase the little scribbles.
We're very professional.
Yes, of course. Anyways, so here you can kind of see that we have this tiling of rectangles. So the hexagons have become rectangles, and they have a consistent color. So for example, this green one is an X stabilizer in the code, and this edge is a ZZ edge that has to be measured in the code. And the way that the quantum error correcting code works is you iterate through each of the colors and measure all the edges of that color, go on to the next color. And as you do this, the edges that you're measuring happen to build up these stabilizers, which should stay consistent over time. And when they don't stay consistent, you know that there's errors nearby. And with a minimum weight perfect matching algorithm, you can use that to kind of solve for the errors.
Which isn't necessarily obvious a priori.
Yeah, definitely. When I was first implementing this code, I expected it to require a color code decoder. I was surprised that minimum weight perfect matching worked.
Yeah. And I just want to comment this is sort of, I mean, it's obviously very related to the Kittai honeycomb lattice, but it's also very related to the color code. You can think of this as kind of a color code where you've peeled off some of the stabilizers. So I mentioned this in the last video, but there's this nice work by, I think, Ben Krieger and Barbara Turhall, although I'm not 100% sure, where they basically show that if you take the color code and you remove some of the stabilizers, you get something that looks like a toric code concatenated with a 632 code underneath. And this is kind of like continuing that process until you have one color per type of stabilizer. So this is very closely related to the color code as well.
Yeah, so in the color code, you also have a hex lattice, but each hexagon measures like X and Y stabilizers. So it
That's right.
has two of them, which because Z is equal to X times Y, you actually get all three.
That's right.
And so here each hex has one stabilizer instead of two, and it turns out that that still works.
That's right. And the sort of intermediate concatenated code is if you take two of the colors and you only have one type associated to each of those colors.
Hmm. All right. let's go over to the code. So there have been like major structural changes to the code since last time because as you sort of personally experienced, Newman, I kind of hit a wall on the complexity of the code where it was just getting too difficult to make changes.
I mean, we were doing really well, and then somewhere on the 4-hour mark, Craig just started trying things at random, hoping it would compile.
Yeah.
Yeah.
Um, so what I did is I sort of brought in proper software engineering methodology. So for example, I pulled off unit tests. I split out separate pieces and tested them separately. I started using revision control, and that kind of got it back into reasonable land. And what I'm intending to do in this video is just to kind of go over each of the pieces of code with you, Newman. So
Sounds good
maybe,
to me.
yeah. So I guess we'll start.
Disclaimer for all those at home: I don't program in Python at all, so this is going to be interesting.
Yeah. Um, probably the I should go over the utilities first, I think, like the things that make stuff easier. And probably the thing I was struggling with the most was indexing the measurements. So I pulled off this class, MeasurementTracker, for doing that math for me. And what this class does is it has this add measurements method, which you can call and you say like, hey, I just did a bunch of measurements. Here are the arbitrary keys that I associate with them. So you could say like, I measured the string x or the number 2 or the complex number 1 plus ij. It doesn't care what they are. You just use whatever's most convenient for you.
Mm-hmm.
And then it just keeps a history of them. So it says, okay, there was this key that was measured. It was measured at this time or in this ordering, and it puts that into the history of that key. So you can keep saying I measured this key, and it'll make a list of all the times that you measured it and remember them.
Right.
Additionally, you can put in something I call dummy measurements, which are like when you start a code, like you haven't measured the Z stabilizers yet, but if you initialize in 0, you know the Z stabilizers. They're all +1. And so to handle that, you can put in a dummy measurement where you say this. I just assert that this is measured, and when you later ask for the indices of the measurements, it'll give them to you, and just like this will just be an empty one, effectively.
Right.
Um, Also, you can say this is a dummy measurement, but I'm actually asserting that this thing doesn't exist. So, like if you initialize in 0, your X stabilizers are random; they're not projected yet. And so when you ask for the comparison of the current X stabilizer that you have measured to the previous one, and the previous one is like one of these obstacle dummies, it'll instead return none and basically tell you that's not allowed.
So it's just a parity constraint without a measurement.
Yeah.
Okay.
Um, you can also declare groups of measurements. So pretty often we're talking about, 2 measurements making up an edge, or 6 edge measurements multiplied together to make up a hexagon, stuff like that. And this just allows you to say, this group of measurements has this key. And then you can treat those just like any other measurement key.
I see.
And then there's a method for querying it and a method for getting
So
this. Go ahead.
the groups will be stabilizers.
They can be anything you want. I mean, from the perspective of this class, it's just you said, hey, here's a group of measurements. I use it for the stabilizers. I use it for going to the diagram. Like after I do the green round, I'll put like these 3 green edges that are inside, like these 3, into a group that's like, half of the red stabilizer here. And then in the next round, I'll use that group key to complete it with the other half.
And is this code publicly available?
I will make the code publicly available. I'll put it on a repo and link to it. I'm not sure exactly where I'll put it, but it'll be in the video description.
Okay.
Um, yeah, okay, so then there's all these methods for defining that stuff, and then you can query it. So you can ask for, like, here's some keys, what are all the measurement times, or, what are the stim record targets? And I also have a utility method for, like, I would like to create a detector out of these keys, please do that. And if you happen to say one of those, like, dummy keys that's an obstacle, it just doesn't add the detector.
Right.
Yeah. Having this class made the code a lot more simple because effectively I could use the same loop or the same subroutine for creating the initial rounds and the like stable rounds, as we'll see a little bit later.
Right.
Um,
But
the
the class takes care of removing parity, parity constraints that aren't actually there.
yeah. The other class that I defined is what I call the Honeycomb layout class. So there's some data here that I had defined before that is moved to this file, but like this class is responsible for taking your like parameters, like I want this particular size of grid, I want this many rounds, and telling you all the interesting information that you need to know in order to build the circuit. So, for example, here's a method that'll take some coordinate which hasn't been made periodic, like you're on the donut and you add 1, and that takes you technically off the donut, so you wrap it back around to 0 because you went off the right-hand
Yeah.
side. Yeah, so that's what this
What
method.
if you're not on a donut? Are we going to talk about how you do this on not a donut?
That'll be at the end of the video where I talk about stuff that's not done, or
Okay.
stuff that I don't even know how to do, really.
Mhm.
Yeah, and then a bunch of utility methods like, for a given stabilizer, what are the positions of the edges around it that are measured first or second? Where are all of the hex centers, like all the stabilizers? Where are all the edges? Where are all the green edges? Where are all the red edges? Just a ton of stuff like that. And also information like, in each round, where is the observable? And in what basis is it?
Oh, that's
So,
nice. So
yeah.
every edge, or that's a little bit strange, right? Because what is like the 3-body thing that this refers to?
What do you mean by 3-body? Oh,
So
this?
like,
The fact that
yes.
there's 3 here? Ah, so you notice a little bit later I multiply it by the tile diameter, which is like, you know, how many times there's blue going across.
Hmm.
So like this one is a tile diameter of 3, this one is 2. And by 2. So this observable is running vertically and it repeats. So as you go vertically down this column, I think,
Hmm.
the pattern here, it's underscore ZZ. So that's like skip, ZZ, skip, ZZ, skip, ZZ. And it's just a repeating pattern to the observable, and that's all that means.
Perfect.
Yeah.
Okay, so you can write down the observable from each of these cases.
Yeah. Yeah. So I hard coded it. There's 6 cases, so that's not too crazy to do. I could write much more complicated code to try to dynamically figure this out based on the definition of the code, but yeah, this works fine.
Makes sense.
Yeah. Um. Oh yeah, I have these methods that I don't really take advantage of yet for splitting the data qubits into 2 sets. So like, I make like a checkerboard pattern of the data qubits where you like take this, like this one, but not this one, and this one, and not that one, and this one. Like a checkerboard pattern.
Hmm.
And this is like the pattern you want if when you're doing the controlled knot operations to do the parity measurements. If you want one round to kind of slot into the next one so that you like use one part of the checkerboard for the second part of a round and the other part of the checkerboard for the first part of the next round, and then they can kind of overlap.
I see.
I don't actually do it in the code, but I put in the stuff so that I potentially could.
Well,
Um,
we could try and do it live on the video.
no.
Okay.
Yeah, so very, very handy class, and having it split off like this means that I can make like tests for each of the methods and like just do a case by hand and confirm that it agrees with it, and then I can trust it and stop worrying about it, because this is like definitely one of the places where a lot of mistakes were seeping in.
Hmm. So just as like a quick question in terms of video content, are we assuming that whoever's watching this knows about how the observable is evolving by multiplying in different rounds some of the edge outcomes?
We can explain that just to be safe. So I have a little diagram here where we have 2 observables, one of which runs vertically and one of which runs squiggly horizontally like this.
Mm-hmm.
I haven't actually tested this horizontal one yet, but the code currently does the vertical one. Um, along this vertical line, the observable changes over time, but it's always inside of that line. The weird thing about this code is if you try to pick an observable that doesn't change with time, you run into trouble because all of these edge measurements are like different bases and they're like touching the observable in different places. And it doesn't quite work. Like you'd end up anti-commuting with something generally.
Mm-hmm.
So instead what you do is you define the observable and change it from round to round. So like in one round, the observable here, so blue is Z. So maybe in one round it's X, X, like that, and then there's a space here.
Mm-hmm.
So XX will commute with this measurement, but it'll anti-commute with this measurement. So if you're doing the red measurements and then the green measurements, for the first round it's going to work, and then for the next round it's not going to work. So in between, you would want to have done the blue measurements, because when you do those, you can multiply those into the observable. So that would be X times Z, which would transition you to Y. And Y is green. So that transitions you from commuting with red to commuting with green. So by having blue in between, or maybe going in the other order, you end up with this ability to keep, have your observable dancing around and changing from step to step so that it never anti-commutes with what you're about to do.
Right. That's really the trick, right? You just want to multiply in outcomes so that in any step, what you're measuring doesn't anti-commute with the information you're trying to preserve.
Yeah. And there's a very simple way of updating the observable, which is, like I said, the observable runs along some specific path. And the way you update the observable from round to round is you just take all the edges along that path that you measured and you multiply them in. So if you measured the blue edges, then you would go along this path and say, oh, there's a blue edge here. I'll multiply that into the observable, and one here and one there, and so forth.
Right. Perfect.
Yeah.
And that should make the cases previously a little bit more clear what they're referring to.
Yep. Okay. So those are the two big like utility classes, the measurement tracker and the layout class. And then I use them to generate the honeycomb circuit. Yeah, so you can see at the very start, I'm setting up my utility classes and I'm going to use them.
Mm-hmm.
And then I start doing kind of standard stim stuff where I annotate the coordinates of the qubits. Like, this is not necessary for the simulation, but it's nice to be able to look at the circuit and actually know where the qubits are supposed to be if you want to, draw it out on paper or something.
Mm-hmm.
And we start getting into operations. So the noise model that I went with was I basically have a series of moments. And within each moment, I operate on some qubits. And every qubit I don't operate on, I apply idle error to. So I apply single qubit depolarization to anything I didn't operate on. And I do that with a parameter that's just something that I passed in that I call noise. So this noise value would be, for example, like 0.1%.
Okay.
And anything that I did operate on, I just apply some specific error that I want to use. So if I applied a reset, then I'll follow it up with an X error, again with that same noise parameter. Or if it's a Clifford operation, I'll apply single or 2-qubit depolarizing noise, depending on if it's a single or 2-qubit Clifford. And for measurement, I would apply X error beforehand.
Okay.
Yeah, sort of like standard circuit noise model, I think.
Yeah, I guess it depends a little bit still on what sort of 2-qubit Cliffords you're allowing yourself access to, but this makes sense.
Yep. Okay, so then we're basically doing like the intro to the circuit. Like literally we're going to do the first 4 rounds, and that's how many rounds that it takes in order for it to become stable. And here when I say round, in the code I sometimes say sub-round. I'm referring to one set of edge measurements. I'm not referring to a cycle of 3 edge measurements, X, Y, and Z. Just one of them.
Makes sense.
Yeah. So anyways, you can see me here like defining some dummies where I say, okay, yeah, the Z stabilizers start off set, the Z edges start off set, the Y stabilizers, because they're the product of Z edges and X edges, they have their like first half set. So the first time that we measure the other half, we'll project them. Um, yeah, that's all that is. And then this little while loop calls into this handy little subroutine for generating one of the rounds. So we're going to go to that subroutine. And the first part here, I'm just figuring out like, okay, where are all the edges and what are the C knots that I'm going to be doing exactly? Like I'm kind of planning out the rounds and just figuring out what's going to happen. And then I start executing it. So I do the resets on the measurement qubits.
Mm-hmm.
And I also at the same time and switching the basis of the data qubit. So I have this method for if we're going to measure in X, we apply Hadamard. If we're going to measure in Y, we apply a variant of the Hadamard that swaps Y and Z instead of X and Z. And if we're going to measure in Z, we're already in that basis, so that's fine. I'm counting staying in Z as a Clifford operation for the noise, or at least in the comment, because I use the same parameter for idle error and for Clifford error. That's fine.
Sure.
Yeah. In principle, I could fold this single qubit operation that's happening on the data qubit with a previous single qubit operation from the last round, which will be down here at like the end of the code.
Mm-hmm.
But I didn't. It's just slightly more complicated to write it. I was just trying to make something that was simple and correct. So there's slightly more noise than there would have to be because of this. Like I think I might have an extra moment or two in each round because of it.
I see. So can we just talk a little bit about, so the 2-qubit, you're only using a CNOT gate for your 2-qubit gate?
That's right.
And the way that you're measuring different bases is you're modifying the ancilla qubit basis.
That's right.
I see. And you're counting...
But not the ancilla qubit, the data qubit basis.
Sorry, the data qubit basis. So in particular, if you, for example, allowed yourself access to a controlled poly operation,
yep,
that would reduce the total depth of the circuit by a considerable amount.
Not not really. It's if you look at what happens on the measurement qubits, the measurement qubit cycle is reset, then C naught from one data qubit, then C naught from another data qubit, then measure. So it's a 4-step cycle.
Mm-hmm.
The cycle on the data qubits is also, well, each data qubit is involved in 3 rounds, which make up the full cycle that I was referring to with the measurement qubits. Mm-hmm. And if you do that thing you're saying where you have controlled Pauli's, you would have a like a C naught, then an X controlled knot, then a Y controlled knot.
That's right.
And that would be a 3-step cycle.
Yeah.
By having the single qubit operations, I guess I inflate that to a 6-step cycle. So yeah, you're right. I guess you're right. It would get a little bit more compact, but not quite as compact as you might expect from looking at this, where you'd think it would go down by half. It would go down by a third.
Sorry, you just said a 3-step cycle versus a 6-step cycle.
This is a good point.
So
I just do it.
Yeah. Compact, I said.
No. The reason it goes from 6 to 4 instead of 6 to 3 is because you have to wait for the measurement qubits.
Right.
Like, you interact with one of the measurement qubits, and then it has to do 3 more steps before you can interact again, which means there's a 4-step cycle. Also, at least on our hardware, and I assume more hardware, like measurement is the slowest operation by far. And so it's going to be the thing limiting it anyway.
Yeah, that's not really necessarily true in other hardware, but yeah.
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 Oh, I guess it's maybe worth mentioning, like, another huge difference between this code and the previous code is that there are actually ancilla qubits for doing the measurements. So, on each of these edges, I'm picturing there being an extra qubit in the middle that I'm C-naughting onto to do the measurements. So we have a heavy hex layout instead of a hex layout.
Yeah, I think it's just important to mention, Craig, that these small differences in the primitive operations you're allowing yourself, for example, moving from a 6-step cycle to a 4-step cycle.
Yep.
that can have a considerable effect on the error rate and threshold that you end up observing. So, it's just important for anyone who's watching to note that these types of small details, which seem sort of unimportant, are actually quite important when it comes to
Yeah.
estimating threshold.
Yeah, I mean, particularly when I have idle error here, increasing the size of the cycle from 4 to 6 is sort of like taking this idle noise and multiplying it by 3, and this like in one of the moments. And this is one of the things that limits the fidelity, the threshold of the code. Like effectively, if you're multiplying all your noise by 3, the threshold has to go down by a factor of 3. So that can obviously be problematic.
Right. And so I don't know if you're interested in doing this, Craig, but I would recommend later maybe going through and trying this in different noise models just to see, kind of get a range of how it performs depending on these sort of minutia.
Hmm. I'm also not sure how interested I am in that.
Okay. Well,
Uh,
then,
the idea of making the circuit as good as I can make it instead of just saying, oh, I did this because it's simple is appealing to me.
that's what I'm suggesting.
Yeah.
Like folding everything together in the most ideal model and seeing how strong it is.
Yeah. Um, anyways, so yeah, we do the first C knots with, 2-qubit depolarizing noise on the targets of the C knots and single qubit idle error on anything that's not touched. And then the second layer, similarly. And then we measure, and you can see like the X error on the measurement, and idle error, so forth. Switching back. After that's done, we get on to like telling or annotating where the observable is moving and what we're supposed to be comparing based on the measurement results that we got in order to get to text events. So I mentioned before that the update that you apply to the observable is along your observable path, the edges that you measured. And that's what this is doing. It's taking the set of edges along the path, intersecting it with the set of edges that we measured, and saying all of these keys go into the observable. So we go to the measurement tracker and we say, tell me the last time each of these keys was measured, which is, just going to be up here. And yeah. Well, actually, technically, I defined the keys here. Here's where I'm saying to the measurement tracker, here are the edges I'm going to measure, and here's the order I'm going to measure them in. And so like this line is coupled to this line via the measurement tracker. And this is so much easier than it was before. Like you saw before, I had like 3 subtractions and some mods, and I like kept getting them wrong.
I tried not to look at it.
Yeah, so that updates the observable, and then we have to introduce detection events. So when the cycle goes red, green, blue. So when you measure blue, in the previous round you measured green. So you look for like the hex that has green and blue around it, and you just learned that one. So that's what's happening in this loop, is it's just going over those ones that were completed and saying, here's how to complete them. In this first loop, it's basically setting up for next time, where it's saying, okay, you just measured blue, you're about to measure red next time. So let's just, say, these 3 blue edges, we'll just associate them with the center one, but with like a key that includes this half, which is, again, just kind of arbitrary. So you can see me setting it up here, and then the next time I call the subroutine, it's actually going to be red here.
I see.
Yeah. And again, this is so much simpler than it was before. It's like ridiculously simpler. Yeah, so that's what that subroutine does. It handles doing a round. When we call this on the first round, because of how the measurement tracker works and it has these dummy measurements, it'll basically not put any detectors in because it'll find obstacles on all of these values. But then on the second round, it like gets the Y basis ones, and you get some detectors, and like the detectors start showing up as you run it, even though it's so you get this like time asymmetry in how it behaves, even though it's written the same way, which again is so much simpler because I only have to write the code once instead of 3 times.
And the dummy the dummy objects also handle the fault tolerant measurement when you've sort of collected information about half of a stabilizer, but not the other half.
The dummy measurements do not handle the fault tolerant measurement. I'll get to that later. But the way stim works is very like backwards looking. Like you say, I measured this stuff. How do I combine those measurements in order to get stabilizers? And
Mm-hmm.
and so like the way you analyze stabilizers, they kind of emit for measurements and go backwards in time. And what the measurement tracker kind of does is it like puts this past boundary that behaves in a particular way as the measurements get to it.
Mm-hmm.
Kind of, I don't know. That's how I think of it. I don't know if that's makes sense to anyone else. But
I
because
mean,
it has this like asymmetry in time where it's talking about the past and not the future, and so it handles the initialization for you, but it doesn't handle the measurement because one of those is the past and one is the future.
okay. I follow that a little bit.
Yeah. In order for it to work on the future, I'd have to just define detectors as like the resets that they come out of instead of the measurements that they come out of.
Okay, never mind.
Look, I have considered adding to STEM the concept of a retector, which is
That
a reset detector, where you're defining the things to check based on here. If you actually look at like where is a detector sensitive to errors,
hmm
you do that by like having Z observables coming out the back. Uh, you'll oh, I need black, and apparently there we go. So you have a circuit, you have some measurements,
hmm
and a detector is defined as a set of measurements.
Okay.
Um, and you can compute where these detectors are sensitive to errors by like saying, oh, there's a Z observable that comes out here, there's a Z observable that comes out here, and they're going backwards in time,
hmm
or you track them backwards in time. And as they encounter like operations in the circuit, like maybe there's a C naught here, C naught there, like a Z would go through the control. Yeah, that's what I wanted. Uh, a Z observable would go through this control, but when it hit this target, it would propagate onto the other side. Like there's rules for how to move them,
hmm
and eventually they should get to resets where they would terminate.
hmm
So we're sort of specifying this like space-time object by saying its endpoints, but we could equally specify it by specifying its start points. That would work just as well. Um, that there is a trade-off, which is when you specify the measurements, it's very easy for software consuming that to be like, oh, here's the measurements that I multiply together in order to get the detection event, right?
Right.
But it also means that when you're like trying to do error analysis of the circuit, you have to kind of start from the end of the circuit and work backwards instead of forward because you propagate them backwards and you don't know how far ahead to look exactly. So if you had retectors instead of detectors,
Uh-huh.
that would guarantee a certain amount of, oh, I can just read the circuit step by step and I know I don't have to look at the future to know like what's going to be sensitive to which errors. That's all available as I go in order. That is my internal feeling why I would like the concept of a retector.
You should put a vote on this video or on your Twitter. Should I introduce retectors based on this description?
I feel like I would need to have a little bit of a stronger use case. Like I need to like say, here's the thing that it makes work that is tricky without it.
All right.
It's more of an issue for observables. For observables, like if you're streaming a circuit, like suppose someone is sending you a stim circuit over a network and you're simulating it as you get it,
hmm
until you've received the complete circuit, you don't actually know where the logical observable is
True.
because it's only declared at the end.
Assuming it's streaming to you forward in time.
Yeah, of course.
Okay.
Um, whereas if the observable is declared as like, here are the resets that it's coming out of, which is an equivalent description, then you could stream the circuit. Anyways, we got kind of on a tangent there. Right. So you run up to 4 rounds just of this sub round generation because that is how many rounds it takes for you to get into like the stable state. That's where like all the dummy measurements are far enough in the past that you're not going to touch them anymore, and you're going to keep generating the same thing from then on.
Are you
And
throwing? I mean, does that throw out the like the one parent that you initialize in some particular parity,
mhm.
and you can use that information for detector sort of earlier than the other two?
Yep.
Does this throw that out?
This does not throw that out. This is just enough rounds to guarantee that you've used that information, that like it initialized special. The way that I know that is I literally like by hand was just like, okay, what do I know in round 0? What do I know in round 1? Where's the observable? What detection events do I get? And if you look from here, it starts repeating. So that's where the 4 comes from. It comes from me doing this by hand. It also comes from me, in the code being like, if I change it to 3, does it break? And it does.
Excellent. Okay.
I also, as we'll get into in a minute, I worked out all the cases where you do the fault tolerant measurement. Anyways, once you're in the stable state, you can then introduce a loop into the circuit. So like Stim has a concept of a repeating block, and you just say like, okay, how many more rounds do I have to do? I know that the rounds go XYZ, XYZ, so there's like 3 of them that are part of the loop. And yeah, you just set up the loop, multiply it on, and now you're close to the fault tolerant measurement. You're within 3 rounds of the fault tolerant measurement.
Okay.
So this last little loop here is just be like, okay, just do that last round, the last 2 rounds, if there's some, so that we're perfectly on what the user asked for. And then we get into how do we do the fault tolerant measurement. So you remember that method that told you where the observable is?
Mm-hmm.
We call that to get where the observable is, and based on the basis that the observable is, we switch all the data qubits into that basis. So if the observable is currently in the x basis, we're going to measure all the data qubits in the x basis. If it's y, we're going to measure them all in y. So we do that switch, and then we measure. And then comes the actually pretty tricky part of exactly which detection events do you define based on those measurements. Because it's very similar to the initialization case where the main difference with respect to the initialization are, first of all, we don't get to guarantee that we end on Z. When we initialize, we always initialize into Z. Whereas for this fault tolerant measurement, we have to handle the X and Y cases as well. So that immediately like triples the amount of stuff that can happen. Additionally, there are actually 2 different Z cases. So like there's this Z case and there's this Z case, and you actually have to treat them slightly differently. And the reason that you have to do that is if you just measured the Z edges, normally when you measure Z edges, you're using that to complete a stabilizer here, right?
Mm-hmm.
So if you just measure the Z edges last round, then this stabilizer was completed last round. And when you measure the individual Z operators and you put them together into edges, it's not really the right thing to do to say, oh, I got this stabilizer again. Instead, what you have to say is, I got this edge again. So you don't compare the stabilizers, you compare the edges.
Okay.
But if the previous round had been green instead of blue, then you would be actually completing the stabilizer. So like, where do I have this written here? So you can see I'm saying if the last measurement basis is the same as the observables basis, then I do one thing. I want to check that the parity edges that I did last time are the same as the individual measurements that I got. Like if these 2 Z's were supposed to disagree, then they should still be disagreeing.
Okay.
But if it's different, then I have to form the hexes. And when I originally wrote this, I thought I didn't need this case, and I just put this case in, and I lost, I'm going to say, several hours to trying to figure out why I wasn't getting fault tolerance. Like why did I keep finding errors at like distance or at tile diameter like 7? There would be there'd still be errors.
Like a
Which is like,
single error that would flip the observable.
yeah. And yeah. Anyways, that's actually what forced me to write this all out. Where I was like, okay, here's exactly what I know. Here's how I
Can
get
you
this
just
stabilizer.
sorry, Craig, I'm a little bit lost. So, can
Sure.
you describe like the wait one error that would happen if you didn't have the first case? Like if you treated everything using the else in that if else?
I actually can't. Uh,
Never mind.
I never did work out exactly what the error was. I knew it was in the last round. I think it was like you just measured ZZ,
Mm-hmm.
and then there was like an XX error on it. So the XX error here would
I mean, it commutes with the edge, but doesn't commute with the plaquettes.
the problem was that like I wasn't getting the relevant plaquette. So XX here commutes with this green one, and it um oh, okay. So you remember there were two cases for where the Z operator could be? Where's that method? So there's this one and there's this one.
Sure.
Suppose that XX edge, or suppose that edge is right here. Then that XX error, when you have this observable pattern, is trivial. It doesn't matter. It commutes with the observable. But here it
Okay.
doesn't. Here it anti-commutes. And basically you don't get a detection event if you don't do it the way that I did it. It could also be that I had another bug in the code where I was like forming the wrong stabilizer. But my best
just
my best guess as to what was happening is I was forming a stabilizer. I was forming a detector,
mhm.
but I don't have anything that actually checks that the detectors are local and that they don't span across the entire circuit. So I was accidentally defining a detector whose error sensitivity went all the way from the fault tolerant measurement to the fault tolerant initialization. And it turns out that this just doesn't work. Like this just like makes some of the edges hyper edges, and I have things that like throw out hyper edges randomly in the conversion to the decoders, which is definitely not safe. But I think there were a few factors that I could have caught this and was missing it. But
Okay.
ultimately, what it came down to was I had to do each of the cases by hand, and I know that it's important to do this. I don't necessarily know exactly why it's important. I just know that I had to. Yeah. Like
Exercise for the
yeah.
viewer.
Yeah. It's perfectly plausible that if instead of comparing the edges, you just did the stabilizers again, then maybe the graph works out.
Mhm.
Um, for like my personal experience of doing it, the main thing was like after I'd worked this out, I probably would have written that correctly instead of incorrectly. I'm not sure. I haven't tested it. Anyways, you have this complicated one, and then you have this easier one where you just say like, I just got all the Z measurements. There are Z stabilizers. I will just multiply my 6 Z's around each Z hex. Uh, like I'll just multiply this into this, into this, into this, into this, into this, like all these 6 ones to get this. And that one's always the same, thankfully.
All right. I'm happy with that.
Yeah. And then you say like, oh yeah, and here's where the observable currently is. And that's the whole circuit. That does fault tolerant initialization. That does the measurements using Ancilla. That does fault tolerant measurement. Um, you can kind of see down here that I'm actually running data right now. I will.
We need to stall.
No. I'm just gonna kill these. It's fine for me to kill them. I had them concatenating into separate files. Oh no, actually, I should talk about the decoding strategy first. So that's how you generate the circuit, and now there's still the like, all right, how do you sample from it and how you decode it in order to compute a logical error rate? So I had this method, sample decode count, correct? Sample, pronounced sample pause decode pause count correct.
Okay.
It takes this parameter use internal decoder. So one of the major changes from last time is, as you know, last time I was using pi matching, and I was running into issues where I was going to sizes that were too big for it to handle because it uses this strategy where it wants to make a graph over the detection events, but doing that does like an all-to-all path search. And it does allow you to truncate it, but I don't really know how much to truncate. And basically, it ended up being that like it was taking hours and hours and hours to run some cases. Whereas when I use this internal decoder, which we'll talk about more in a second, that those cases instead take like seconds or minutes. Right, but yeah, we'll get to that in a second. How does this method work? This method works in a way where it does not trust the decoder. So first, it uses stims like built-in functionality to sample the detection events in a circuit as well as the observables. And then it splits those two things apart into the detection events and the like observable logical frame changes that it saw. And then it only gives the detection events to the decoder. It does not give the decoder the frame changes. And it's the decoder's job to predict the frame changes from the detection events.
Okay.
Yeah.
What is the format in which it presents the detection events to the decoder? Does it matter?
It depends on the decoder. For pi matching, it like uses pi matching's Python API to define a network X graph that corresponds to the error model and then gives it as a NumPy array.
Okay.
Whereas for the internal decoder, we write out like stim's detection event file format.
Okay.
Yeah, but I want to focus a little more on the significance of not giving the decoder the frame changes. So the decoders can have functionality where you give them the frame changes and they'll like compute for you whether or not they got it correct or not. And because we're writing in Python and the decoders that we're using are in C++, that would be like way faster for computing the differences. But it also relies on having a certain amount of trust that the decoder's not cheating, that it's not going to have a bug that just causes it to say like, yep, I got everything right. It's all good.
Indeed.
So instead, I'm being a little paranoid and saying, no, you must give me the predictions. I will handle comparing them. So that's what this code is doing. It's just saying like, were there no differences in each of the shots? So if you have multiple observables, you have to get all of them right, and then it just counts how many times that it got it. Yeah. Anyways, so last time, this pi matching code is basically the same as it was last time, where like I said, I converted it into a network X graph. Definitely the best thing about pi matching is it's very easy to interface with it because it takes network X, and that's kind of a well-known Python library.
When you say you convert it into a network X graph, you're assuming that every error results in a like an edge-like pair of detections.
This is true. So actually, in the conversion, I just throw out more complicated edges instead of using them. I can specify this argument where stim will try to make sure that every error is described in terms of components that have at most two symptoms. So you have like more confidence that it's a graph. Actually, as part of writing this, I found a way that components with 3 symptoms can get through this in some cases, and I'm gonna like fix
That's
that.
scary.
Yeah. But one of like part of the reason that I did this weird code is because it's like an excellent test case for software that I've written internally, and just to make sure that it generalizes. Like you flush out so many bugs when you try a different case, and you increase your trust in the software correspondingly from like 30% to 31%.
But so it's a small, it's convenient that in this case matching was a valid way of decoding.
Yeah,
There's no reason to
yeah,
expect it to be
yeah. If you
pure.
if you watch the last video, you can see the moment where I'm like, wait, all of these errors have 2 symptoms. Is matching gonna work on this? Like I did not see that coming. Even though in the paper they're like, yeah, there's like this toric superlattice or something.
Yeah. Okay. Well, that's great though.
Yeah,
So we're using matching decoders and it works.
yeah.
Excellent.
And so here's the method where I'm calling the internal decoder, which is just this binary file that I've copied into the directory. Like I can't really say a lot about it, but I didn't use it last time because I wasn't even sure if we were allowed to show like performance characteristics. But I asked the guy who made it, and he said it's fine. So this internal decoder is written by Austin Fowler. It's a minimum weight matching decoder. It uses sort of the same general approach that he like has published before, where the match it's not quite correct to call it a minimum weight perfect matching because it's not a perfect matching because not every node is involved in the matching. It's not even technically a matching because you're not picking edges that match nodes, you're picking paths that match marked nodes. But anyways, it uses a slightly different algorithm than the normal one, specialized to the error correction case, and it has much better scaling. It's like roughly linear in the number of detection events with, the worst case, that's expected time. The worst case can be pretty bad still. Like minimum weight perfect matching is a terrible worst case runtime. Yeah, I make these files in a temporary directory. I say like, yeah, run on these files. It writes out a file, and then I read that file. That's what it does.
I see an ignore distance one errors. That's kind of scary.
So normally this decoder, if there's a physical error mechanism that has no symptoms but flips the logical frame, it'll say that's not okay. You can't correct that. But here, if I'm testing an extremely small distance and I just want to draw a curve through the distances, I might actually want to see that case. Like I want to see the case where it fails at distance 1.
Okay.
Yeah, so this one makes sense to me. This one is a lot more worrying, to be honest. This one is like, yeah, if there's a degree 3 edge, degree 3 error in there, which is potentially very significant, just, yeah, never mind.
So just to talk a little bit more about this case, I mean, we've talked about this before. In this for this particular code, you do have hyper edges,
Yep.
detection events, but it just so happens that those hyper edges can be decomposed as pairs of edges that are also, manifest from other errors.
Yeah, like, for example, if we found an error before that like there is an error here. If you have a Z error on this qubit, it'll set off this stabilizer and this stabilizer. So that's 2. And if it's combined with something else, it can also trigger measurement errors in blue, I think. I don't really remember it.
Yeah, I mean, if it happens in between measuring the green and red.
Yeah, right. Yeah. Because blue is the product of green and red anti-commute with a blue error. If you sneak the blue error in between half of the edges being measured and the other half, it'll flip this stabilizer like temporarily, and then it'll go back. So you'll see 2 changes. And additionally, because blue anticommutes with green and red, it will permanently change these 2. So that's 2 more changes. So that's 1 error that causes 4 changes, 4 detection events. But
So yeah, sorry, go ahead.
yeah, but it like obviously decomposes into, oh yeah, there's the error that flips these 2, and then there's the measurement error that flips this one, then flips it back.
So it's a little bit of a small miracle that all of these hyper edges decompose as edges in the error graph.
Yeah.
So you're okay, basically.
Yeah. And I'll definitely say like these errors aren't necessarily intuitive. Like Newman and I discovered them together with like predicting that they couldn't be there.
Yes, it was an adventure.
Yeah.
But it works. The error goes down, everything's fine.
Yeah, so that's kind of all the code. I mean, there's this conversion method to make this network X graph. I guess also there's the main method which is like does the plotting and does the stuff where it says like, okay, run these cases, write them to a file. But that's kind of all glue code that doesn't really matter. So I'm going to take that data I was running, which is writing into 2 files. I'm going to concatenate the 2 files. The file format is super simple that I save. It's just a CSV file where I say like, oh yeah, here's the size I was running, the time size, the error rate. Here's how many I ran, and here's how many were right. So I can just take this data and I can concatenate it to the bottom of another file in order to combine them. Like so. Get rid of that one. And then I can say, I would like to plot it, which I currently do by saying take no shots, keep the data and plot afterwards, which is not is a very weird workflow. I should really make that better, but it works. So here's what we got.
Wow, you're getting up to pretty big sizes.
Yeah. So this was definitely the advantage of switching to another decoder. The amount of time that it took to run this was less time than it took to do the plot from last time. Which maybe I can find.
Is the logical error rate in terms of the round, the logical error rate per round, or logical error rate per block of 30? It looks like from the key on the right.
Oh, I should really have that in the title. It's per round.
Okay.
Or per sub round, I should say. I say sub round instead of round to make sure that I'm avoiding ambiguity between the 3-round cycle and the individual rounds making it up.
Also, I noticed just like a little bit concerning is the green curve there on the right key looks like it's distance 13, but it's in the middle of a lot of
Oh, no, that's 3.
never
Yeah,
mind.
so
Never mind.
one of the confusing things about this is I actually sampled up to higher sizes at low errors, but they're just way off the bottom of the graph. Like I think they're all 0.
Okay.
Yeah,
Those were
I
sampled
should
at
really remove those. I could go into the CSV file and delete each of those, but whatever. For reference, here is the one from last time with a different error model. So, what is the best way to be able to actually see this? I guess I'll make it full size. So with the other error model, which was just, first of all, there were no ancilla in this one. There was no measurement error. You were just going over the pairs and like directly measuring the XX parity. And the only source of error was 2-qubit depolarizing error on each parity measurement.
Mm-hmm.
Also, this previous one doesn't have any noise at the start or the end. So it's noiseless prep and noiseless measurement. Anyways, with that one, we saw the threshold was around like 3 to 4%. That's where they're crossing.
Mm-hmm.
With the new noise, we had a bet actually about whether it would be above or below 0.5%, where I thought it would be above, and Newman thought it would be below. And Newman
feels good to be right.
Newman might have more experience with understanding the behaviors of these things than I do, because 0.5% is right here. And which side is this on? Is this on the left or the right?
I think it's on the left.
Yeah. Are you sure? Are you sure?
I'm fairly sure from my experience with error correction and threshold graphs. That is, in fact, the left of that line.
Okay. Yeah.
However, again, encouraging you to try sort of the best case where you assume whatever Clifford operations you need to fold the rounds together as much as you can.
Oh yeah, that could make the difference.
That could make the difference. So it's really your own fault. It really, I mean, I will bet you. I will have a second bet, which is that I would guess it's still below 0.5, but greater than 0.4. I feel like it's a pretty nice bet.
I'm not going to take that.
Come on.
Nah.
Right.
I have enough motivation to try to make the circuit a little better now, I think.
Fortune favors the bold, Craig.
Yeah.
It's fine.
But yeah, I guess the other thing to sort of discuss is what's not done yet. So, things that are not done. The circuit is not compressed yet. Okay, we were just talking about that. Also, there's supposed to be 2 observables. Like, in order to have an error correcting code that's quantum, you need to have 2 anti-commuting observables that you preserve. And I haven't actually tested this one yet. So I have to add that one. And I should probably even have a test where they're both in the system simultaneously. Like I prepare Y instead of X or Z, for example. To be
also understanding the scaling at a reasonable error rate.
What do you mean?
Like, internally or like, pretty externally here, we care a lot about these lambda factors, which is this error suppression at the error rates we're trying to hit. We don't care directly about the threshold, although it can sometimes be a proxy for this.
Yeah. Yeah, that is true. Like we would like to essentially look at a given error rate, and as you increase the distance, say, what is the factor reduction that you're getting? Like here, it kind of looks like maybe they're getting closer, but that might just be a low distance effect here. Yeah, where essentially you just pick some error rate, and then you start increasing the distance and you see how it affects the error rate. And do you get like 10x reduction for each increase in distance, or 2x, or what? And we call that lambda.
Right.
And for
And verifying that verifying that you're achieving the full code distance.
yeah, I was also thinking that we could check, like personally, I think that we should check how many physical qubits do we need to hit a particular error rate. I know that that's like a very specific question, and it has a lot of assumptions going into it. So I came up with a name for it, okay?
Okay, hit me with it.
So I was thinking, to do a quantum computation that's kind of like with like a non-trivial quantum computation, like a factoring computation, a chemistry simulation in a fault-tolerant computer, you need like a billion instructions. You need like 1,000 qubits, logical qubits.
Okay.
So I tried to find a word that had like BI for billion, and TH for thousand, and so forth. And what I came up with was bistoque. Okay. All right. I'll just write that out. Bistoque. So billion, billion,
Recording.
billion step, thousand, just O doesn't matter, qubit, and then there's an E, and this is pronounced like bespoke.
Okay, I'll tell you what I think about this after you turn off the camera.
So I think what I would like to do is I would like to see how bespoke is this code. You know, does it
Oh my
is
God.
it meet the, like, how many qubits does it need in order to be bespoke?
I mean, given that we don't even know how to do logical gates on this yet.
Yeah, but basically you would assume that a logical gate takes roughly distance d,
All
or
right.
like d rounds. You're right. It'll be an approximation, but it's already so specific that
So bespoke
yeah, you
or
get it.
stoke.
Yeah.
Just how would you how are you what's the idea for using this in like the common parlance? What would you say like the bestoke of the surface code is 20 million or something? Can you use bestoke in a sentence for me?
I haven't worked out all the phraseology, Newman.
Any of the phraseology? Okay, fine.
What I did picture was that you would have a plot where you had physical error rate along the bottom and like physical qubit count along the vertical, and then
Mm-hmm.
you draw a line for where you hit the requirements through it, so it would like look
I
like
see.
this, and then you like shade the region over here, so like here is where you're inside the bespoke regime, so
I
you need at
see.
least this quality or this quantity. That's the idea.
Oh man, now that you explain it, I hate to say it, but I kind of like it.
I know, right?
All right. Anyway, I feel like we're getting off track here.
um I guess, what else is there to discuss? Did you want to turn this into a paper? Do you think that we could put this in a paper?
I mean, depending on how much more work you want to put into it, probably. I feel like I feel like maybe we should not discuss this on the camera because we don't.
Or
There's so
like,
many
yeah,
questions about this code, right? Like in particular, the fact that in my mind, from my understanding, which is still very limited, the sort of inelegant boundary conditions pose a serious problem for designing this practically.
yeah. I mean, we would say that. I think it's fine for us to discuss what about this is conducive to a paper and what's not.
Yeah, so I think that this code, I mean, I can't speak to exactly why, what specifically the original authors had in mind for this code. I assume it's, for a Majorana type qubit architecture where your native operation is 2 qubit measurements. But it also could have some value for a lot of these codes which are looking for these sparse connectivities.
Hmm.
In particular, if you have a lot of for superconducting qubits, if you have a lot of frequency collision, sometimes it's nice to design sparse lattices. And this has been like a whole big effort. In part, IBM has, as we've talked about, or as I think we've alluded to in the commentary, this heavy hex lattice. Finding codes that are well suited to this lattice, I think, has value.
Yeah.
Uh, their current proposal is like it's interesting. It's like got a nice threshold on one side, and on the other side it doesn't have any threshold. There is another paper
Sorry,
by
which proposal were you referring to just then?
this heavy hex code that they have.
Ah, okay.
Yeah,
Which side has a threshold and which doesn't?
I mean, it doesn't matter. Z or X, pick your poison.
Oh, wait, really?
It has a threshold against one type of error, not the other. One type of the code you can think of as like, if you abstract away the connectivity and the details, it's sort of like you take the Bacon Shore code and then you gauge. My understanding is you take the Bacon Shore code and you fix
I
uh,
see.
the stabilizers of one type to like turn it into half a surface code.
I see. So basically you're saying that like in one basis the stabilizers are like a checkerboard pattern, and in the other basis the stabilizers like stretch across the whole thing.
That's my understanding.
And so because the number of qubits making up the stabilizers keep getting bigger, they get more and more noisy until they stop working.
That's right. So if you have, if one of your noise sources is particularly damaging, you can sort of choose the right side for that noise, but you might have problems scaling it up.
Did you want to make any predictions on whether or not IBM jumps on this code here that we're looking at compared to
I
HeavyX?
this is came out 2 weeks ago. I have no idea, but it's
Yeah,
a nice code. I mean, I really like this code.
yeah,
The one obvious issue that we've already brought up is the fact that it's defined with periodic boundary conditions.
yeah. We can talk about that a little bit more. So in the paper, they mention boundary conditions, which I can go to the figure here. Yeah, so like that you try to terminate it like this. But you run into trouble because the way the logical observable is defined, as you go through the cycle, you end up with some point where you have a single qubit observable here and nothing there, and you're about to switch from like measuring X to measuring Z or something, and you don't have any edge that you measure down here to multiply into it to switch the basis. And so it's going to anti-commute with the next round. So you have to pull some sort of shenanigans in order to fix that. And the authors don't know how to do it without paying some costs. I don't know how to do it without paying some costs. Maybe you have to pay costs. Like I tried to figure out how to put boundaries in for hours, and the best I found was like putting in like 4 body measurements for these twos and 4 body measurements in the zeros as part of the product, and it got complicated. I'm not sure it works, and it kind of ruined the like one of the really nice things about this code is you can run it on a heavy hex layout or you can run it on a hex layout.
Where your qubits have at most degree 3.
Yeah. And if you put these boundaries in, all of a sudden you like lose that property, or you lose the 3 round structure of the cycles. Like you have to put in some gaps where you have time to do these 4 body measurements. And even with those, I couldn't figure out how to put it a on a square instead of on a cylinder. Like it only fixed one of the boundaries.
Yeah, that's still pretty problematic.
Yeah. Like I know I'm being sort of vague about the details here, but basically it comes down to like I don't know how to do the boundaries. If if you know how to do the boundaries, that's a paper.
I do not know how to do the boundaries. I'm sorry.
Yeah.
I mean, the authors do give like a prescription. I'm not sure if they're totally satisfied with it. I haven't really absorbed that, so I don't want to speak to it too much.
Well, I mean, we did contact them and ask them about it, and they did say like, okay, here's what we know how to do. Here are the costs to it. We don't how to essentially we don't know how to not pay these costs.
Right.
So like to them, it is still an open problem how to put nice boundaries in. I think that's a fair thing to say.
I agree.
Yeah.
Um, yeah, I mean, I think that the things that are at least the obvious simple thing left to do would be to try and design a compactified syndrome circuit that hadn't minimizes the number of idle operations.
Yep.
I bet you that this pushes. I mean, I'm happy to take another bet with you, but apparently you don't want to. It's fine. I don't mind.
Maybe I've learned my lesson.
I'm tired of being right.
Uh-huh. All right. If you can't think of anything else to say about it, I think we can end it here. Like I'm pretty happy with that.
No, nothing to really say except this is a really cool code. I love it. Like I think a lot of people have thought about the Honeycomb model before, building a subsystem code out of it, and a lot of people ran into the same problem, which is it's hard to encode macroscopic degrees of freedom on that lattice. And I think this is a really nice solution. And B, I think your code is awesome, man. it's really cool that it does this, and it's really cool that you can get this done in like.
Sorry, did you
Oh,
just switch meanings of code? You went from the quantum error correcting code to the software?
I did.
Ah, okay. Anyways, yeah, continue.
I am really impressed with your software and its ability to handle this case, and in particular, handle it with minimal revision and very quickly. So
But yeah,
congratulations on getting
yeah,
good software. This is like a good advertisement for STIM. If you're interested in the Clifford simulator, I strongly recommend STIM. It's really good,
yeah.
especially for error correction.
Well, thank you, Newman.
You're welcome.
I will go on record as being like, if someone solves the boundary issue for this code, I think IBM jumps on it. I think they use it.
I have no. I mean, I don't know what they're. I don't know. I have no idea. It's a nice code. They have a lot of nice codes too. You'd really have to look at the specifics. I mean, when we measure, I mean, it's important to note that when we like do these sort of simulations, we have this incredibly contrived noise model that looks nothing like at least what like
Yeah,
I think of as a superconducting error model. And so when we say, these like single qubit, like for example, these idle errors that Craig was inserting, in practice for us, we would not care that much about a single qubit idle sort of idle round. Like that's not a
it de
dominant source of noise.
well, it depends if it's in tandem with a measurement or not, because our
Single
measure.
qubit, single qubit. When I say single qubit, I mean like like a Y rotation or something.
Oh, the Clifford rotation error.
If you have
Yeah.
like 30 seconds of waiting, I mean it's rough and you want to cut them down, but it's not the end of the world.
Yeah, like currently, almost all of our error, or like a huge majority of our error budget, or budget's not really the right word. Error accounting is just our measurements take long enough that the data qubits are depolarizing a lot, or dephasing, or decaying, or whatnot. And yeah, so this code, yeah, like one of the reasons that this code is interesting to me is the fact that the measurement qubits, like you're like kind of running them in tandem. So like
Mm-hmm.
if we tried to run it on our hardware, maybe the cycle is surprisingly fast in comparison for hardware where measurement is long compared to like the 2-qubit operation. This code has that benefit. On the other hand, like this threshold is not as good as the surface code threshold, which is a little uh, problematic, I think.
Yeah, I mean it depends on a lot of specifics that aren't captured in this very theoretical noise model. But I think it's a good starting point. It's definitely interesting.
Yeah, the surface code threshold is like over here, right? Like around here for circuit noise.
It depends on the specifics of the circuit noise, but it's roughly between 0.5% and 1%.
Oh, so like here-ish.
Yeah, it depends on exactly what you're assuming.
Yeah. Okay.
Yeah. All right. Thanks for inviting me, Craig. This was a lot of fun.
Yeah, I enjoyed this a lot more than you watching me fail to code for 4 hours, to be honest.
Me too, as it turns out.
So maybe we'll do this again sometime. And
Yeah,
I would be interested in turning this into a paper. So maybe I'll fix that up and we'll talk more about that offline.
sure.
Yeah. All
Sounds
right.
good.
All right. Thank you for coming,
Bye,
Newman.
everybody.
Yeah, thanks for watching.